Hello everyone, welcome back to another StudyingWorks video. In this video we will be covering the concept of enthalpy and the concept of equilibrium and how they relate to balanced equations. If you haven't watched our balanced equations video already, make sure to watch it. The link will be in the description and it will also be in the card above. Anyways, let's get into the video. First, each chemical reaction has its own enthalpy value, represented by delta H. Enthalpy is the heat of a reaction, which can be represented by a positive or negative value. If enthalpy is positive, the reaction is endothermic, meaning the reaction takes heat as a reactant. If enthalpy is positive, the reaction is exothermic, meaning the reaction releases heat as a product. Let's look at an example of this. Here, we can see we have our equation, and real quick I'm going to balance it. If you want to practice, you can pause the video and balance it, but here's how you would balance it. And now, right here, we can see this delta H value equals 35 kilojoules per mole. That means for every mole of reaction, so typically there would be an RxN, but we don't write it when representing the value of delta H, but just imagine there's an RxN there. So for every mole of reaction, we are having 35 kilojoules of energy. And now how will we know whether it's being released or whether it's being taken in? So for here we can see there's no negative value, meaning it's positive. And if we remember from before, that means it's an endothermic reaction, meaning heat is a reactant. So the reaction will be using heat, meaning it is taking in heat. Now, if this were a negative sign right here, then heat would instead be a product. And in that case, energy would be released for every mole of reaction. Now, in other cases, we may also see that the delta H value is not given to us, and instead, heat will be described in the equation. And so, in this case, we can see heat is a reactant, meaning it is endothermic, because, as we know from before, if heat is being taken in as a reactant, it has to be an endothermic reaction. And now, if the heat was instead moved somewhere here, then we would be looking at an exothermic reaction. And so that is how we would find delta H values, or whether a reaction is endothermic or exothermic. And now, finally, the question you may be asking, the question I said we would answer in the beginning of the video is, how does this all relate to equilibrium? And now, here's why. Most reactions are reversible, meaning that the products can actually be used to make more reactants, meaning these products right here, I can take them in and I can make more hydrochloric acid or more solid magnesium if I wanted to. Now, when the rate of the forward reaction is the same as the rate of the reverse reaction, or the products changing back into reactants, we are at a state of balance, or equilibrium. And when the system is at equilibrium, we know that the reverse reaction and the forward reaction are happening simultaneously. It's just that we are not able to see this because it's only a chemical change, not a visual change. And so, if the system is at equilibrium, we can infer that the reaction is indeed reversible, allowing us to draw double arrows here. So whenever you know that a reaction is reversible, imagining that both of these are reversible reactions, then you can draw a double arrow right here to represent that the reaction can go both ways. Thank you for watching, and I'll see you in the next video.